Welcome, everyone. We are jumping straight in today, really getting into the foundations of modern AI. And this is actually the start of a brand new series for us. Welcome to the Before AGI podcast, episode 1 of The Minds We're Building. So our mission today, it's pretty crucial if you're looking to use AI strategically, right? We're essentially peeling back the curtain. We want to explain the absolute fundamentals, like how these systems actually hold on to knowledge. And what was that big breakthrough, that architectural leap that gave them this huge power boost? And maybe most importantly, how does their way of thinking, if we can call it that, really differ from how humans reason?
Exactly. I think to really get a handle on the capabilities and, maybe more importantly, the limitations of today's AI from a strategic view, you really do have to look under the hood. We need to get past the buzzwords and actually examine the mechanics inside the weights, these vectors we hear about, and definitely the attention mechanism. That's how we can grasp why modern AI is so good at spotting patterns, but, well, it's still fundamentally missing what we'd call real reasoning.
Okay, great. Let's unpack this then, starting with maybe the most basic question. How do these machines actually store knowledge? Because, when we think of knowledge, we think of facts stored somewhere specific, like in a database, right? But a neural network, it's just layers of math functions connected together. So where does the concept of chair or even something abstract like justice actually live?
Yeah, and that's probably the first big mindset shift compared to traditional software development. Knowledge isn't stored as a neat little fact in a specific box. Instead, it's encoded in these really complex numerical relationships, and it's spread out, distributed across the entire network. It's in billions, sometimes trillions, of these internal parameters. We usually call them weights.
Weights. Okay.
Right.
Sometimes people call them dials. Is that a fair analogy?
That's actually a really good way to picture it. Yeah, imagine millions or billions of tiny dials inside the network. And when the system gets trained on huge amounts of data, like reading tons of text or looking at thousands, millions of photos, it's constantly tweaking those dials. It's this iterative process, statistical, really. The network just keeps adjusting the weights until the overall configuration of all those dials lets it successfully recognize the patterns it's being shown.
Huh. So if the knowledge about what a cat isn't in one specific file, what makes the network recognize that pattern as a cat and not, say, a dog?
It's the specific arrangement of all those weights together. That's the knowledge. And the real power comes from the fact that this representation is distributed, spread out. So instead of storing cat in memory slot A1, it represents cat as a unique numerical location, a point in this incredibly high dimensional space. And the really clever part is that concepts with similar meanings like kitten, feline, maybe whiskers, they end up having numerical locations that are very close together in that space. We call these numerical locations vectors, or you could think of them as numerical fingerprints.
Right, so the system figures things out, not because someone wrote a rule like if it has whiskers and purrs, it's a cat, but because the vector for cat is mathematically closer to lion than it is to truck. The knowledge is sort of blended together, which makes it more flexible.
Exactly. It's blended. And because of that, if one tiny part of the network, one little weight, gets damaged or fails, the whole concept of cat doesn't just disappear. It's still represented by millions of other related weights. This distribution gives it amazing generalization ability and robustness. That's why these AI models don't need to be explicitly told the dictionary definition of every single word. They figure out the meaning from context, from where that word's vector sits relative to all the others.
Okay, that makes sense for the learning part. But I remember early neural nets, things like RNNs, recurrent neural networks, they still had a really hard time with long pieces of text, didn't they? Like, they were okay with short sentences, but seemed to forget the beginning of a paragraph by the time they reached the end.
Oh, absolutely. That was a huge roadblock. It almost stalled progress for a while. These older models, they processed information strictly one word after another, sequentially, which first off made things incredibly slow because you couldn't process words in parallel. And second, it created this infamous problem called the vanishing gradient problem.
Vanishing gradient. Okay, that sounds pretty technical. For listeners maybe not deep in the math weeds, what does that problem actually feel like for the model? What does it mean practically?
Think of it like contextual tunnel vision. During training, the signal that tells the network how wrong it was, the error signal or gradient,
Yeah.
it gets weaker and weaker as it travels backward through time, through that long sequence of words. By the time that correction signal gets all the way back to the beginning of a long paragraph, it's practically zero. It's vanished.
Yeah.
So the network effectively stopped learning from or even caring about the context from way back at the start. It made it impossible to handle complex connections across long distances in the text.
Like understanding a pronoun, say he, when the person's name was mentioned 3 paragraphs ago.
Precisely that kind of thing. It just couldn't hold on to that long-range dependency.
So they needed a fundamentally new architecture, right? Something that let the system kind of look back and connect distant pieces of information directly, not just step by step. A shortcut.
And that brilliant shortcut was the attention mechanism. It came out in that really groundbreaking 2017 paper, Attention is All You Need, which introduced the transformer architecture. This wasn't just a small improvement. It was a total game changer, a paradigm shift. Maybe think of attention like a spotlight in a dark theater. But, and this is key, the brightness of that spotlight can be measured. It has an intensity.
Oh, I like that. A spotlight. So it's actively deciding which bits of information are most important at any given moment.
Exactly that. Instead of just processing words one by one and giving them equal importance based on position, attention lets the AI dynamically calculate an attention score. It calculates the score between every single pair of words in the input. This score basically says, how relevant is word A to word B? Quantifiably. So the AI can look at the current word it's processing, maybe the word it, and instantly shine its spotlight, give a really high attention score to the specific noun it refers to, even if that noun was, say, 50 words earlier in the text.
Okay, walk us through that example you mentioned, the word bat. How does attention help figure out if it's the animal or the sports equipment?
Sure. So the model sees the word bat. Ambiguous, right? Attention immediately kicks in and calculates these relevant scores with all the other words nearby or even far away. If the surrounding words are things like swing, pitcher, home run, those words get very high attention scores in relation to bat. And the model instantly weights the interpretation towards sports equipment. But if the surrounding words are flu, cave, echolocation.
The spotlight shifts.
Exactly. The attention scores for those words become highest, and the model weights the interpretation towards animal. It figures out the meaning based on calculated relevance, not just word order.
Wow. And this wasn't just clever theory. It had massive practical consequences. This is what really enabled the current AI boom, isn't it?
Absolutely critical, because attention allows for parallel processing. The model can calculate all these attention scores for all word pairs at the same time. Instead of one word after another, it slashed training times dramatically. And that scaling ability, that speed up, suddenly made it feasible to train these gigantic models with billions, now trillions of parameters. That's how we got today's large language models, LLMs like GPT-4. The transformer architecture, powered by attention, was perfectly suited to leverage modern computing hardware. It just accelerated everything.
Okay, this is where it gets really interesting for me, because we know how they learn, how they store knowledge and weights, and how attention lets them focus. But now we need to talk about the crucial limitations, because even with all this power and scale, the experts are pretty clear. These systems are not thinking like humans.
Yes, and this is probably the single most important distinction for anyone making decisions about AI or using it. Today's AI, even the most advanced, is fundamentally a world-class, highly sophisticated pattern-matching engine. It is not a system capable of what we call genuine human-like reasoning. It doesn't understand cause and effect, it can't really think counterfactually, and it certainly doesn't possess consciousness.
It sounds a bit like that old idea, Moravec's paradox, right? The things that are super easy for computers, like churning through huge data sets or doing complex calculations fast, are incredibly hard for us. But the things that are easy for us humans, common sense, just walking across a room without bumping into things, understanding nuance, those are still surprisingly difficult for AI.
That's a great way to put it, and that difficulty really stems directly from its statistical foundation, how it learns from patterns. The first big limitation is this confusion between correlation and causation. AI is brilliant at spotting that two things happen together often, that's correlation, but it doesn't understand the why, the underlying mechanism, the cause.
Right, the classic example people use is the one about hospital data, isn't it?
That's the perfect illustration, yeah. Imagine you train an AI on millions of electronic health records. It might find a very strong statistical correlation. Patients who receive supplemental oxygen have much higher mortality rates. Now, if you just ask the AI, based on that pattern, how do we keep people healthy, it might wrongly conclude that giving oxygen is harmful. It fails because it lacks the causal model a human doctor has. Oxygen isn't the cause of death. It's administered because the patients are already the sickest. The AI sees the pattern but misses the underlying reality, the intent.
And that inability to model the real world, that lack of causal understanding, that must lead directly to the next problem. Generalization, right? If it only learns patterns, it struggles when the pattern changes, even a little bit.
Yes, exactly. The gap in generalization ability between a human and current AI is just vast. Think about a child. You show a toddler one tree, maybe two. Soon, they can recognize thousands of different kinds of trees in different seasons, whether it's a real tree, a drawing, a photo. That's abstract generalization. True understanding. Now, contrast that with AI. There's research showing models trained only on, say, two-digit addition problems. They get really good at that. But then you give them a three-digit addition problem, they often fail completely.
Wow. So it didn't learn the concept of addition, the abstract rule.
Okay.
It just memorized the statistical patterns associated with adding two-digit numbers.
Precisely. It mastered the statistical structure it saw in its training data, but it hasn't internalized the abstract, universal mathematical rule that applies regardless of the number of digits. And this ties into the third major limitation, the lack of common sense. AI doesn't have this built-in, grounded model of how the physical world actually works, things like gravity, object permanence, or even basic human social and emotional understanding.
So when we see these LLMs generate text, that sounds totally fluent and convincing, but it's factually wrong or just logically bizarre, what people sometimes call hallucinations.
Yeah.
It's happening because it's just predicting the next most likely word based on patterns. It's not actually checking its output against some internal model of reality or truth.
That's exactly it. It's manipulating symbols, words based on statistical likelihoods learned from vast amounts of text. It's not reasoning about the underlying meaning, the context, or the physical constraints of the world. It can generate text that looks like perfect sarcasm, for instance, but it has zero genuine comprehension of the emotional state or social situation that makes sarcasm meaningful to humans. It's a brilliant mimic, statistically speaking, but it lacks grounding.
Okay, so the clear message from the leading edge of AI research seems to be making these models bigger and training them on more data makes them better, faster, more powerful pattern matchers. But this progress, impressive as it is, it's more like engineering refinement on a specific type of engine. It's not necessarily a path that automatically leads to genuine human-style intelligence. The analogy I've heard is like building faster and faster cars. That doesn't mean they'll eventually learn to fly on their own. It's a different architecture needed for flight.
That's a very apt analogy, and understanding that fundamental distinction that these are incredibly powerful pattern engines, not reasoning machines, that's probably the most crucial piece of strategic knowledge you can have right now.
Okay, so wrapping this up, what does this all mean for us, for you listening?
Yeah.
When you're using these AI tools in the real world, what's the practical takeaway?
I think the core implication is to view AI as this incredibly transformative set of tools, tools that augment human intelligence rather than replacing it wholesale. You should absolutely rely on AI for its strengths, its incredible speed, its ability to recall information instantly, and especially its power to find subtle, complex correlations in massive data sets that no human brain could possibly detect. But, and this is a crucial but, you absolutely must rely on human judgment whenever causal understanding is essential. That means for strategic planning, for tackling truly novel problems the AI hasn't seen patterns for, and for any decision that requires deep situational awareness or adapting to ambiguous, fast-changing environments. Those are still human domains.
That's incredibly clear. Okay, let's summarize this deep dive then. We looked inside the machine, saw how neural networks store knowledge, not as distinct facts, but as these robust distributed numerical relationships called weights, which allows for that abstract vector representation. We explored how the attention mechanism, that spotlight, was the key that unlocked modern LLMs, allowing them to manage long-range context and enabling the parallel processing needed for massive scale. And finally, and maybe most critically, we established why today's systems are best understood as powerful pattern matchers, but they're fundamentally limited by their inability to truly generalize like humans, grasp cause and effect, or apply common sense reasoning.
Right. And maybe here's a final thought for you to chew on. As these AI tools get even more powerful, the real lasting competitive advantage won't just go to the people who use the tools. It will belong to those who truly master the synergy, that crucial interplay between AI's immense computational power and the irreplaceable creativity, ethical judgment, and causal understanding of the human mind.
That's a powerful insight to end on. Thank you so much for joining us for this deep dive on the Before AGI podcast, exploring the minds we're building. If you found this discussion valuable, please do hit subscribe wherever you get your podcasts so you don't miss future episodes diving into machine intelligence. And for more visual explanations, tutorials, and some deeper insights into these topics, definitely check out the companion videos over on YouTube. Just search for Ian Ochieng AI. That's Ian, O-C-H-I-E-N-G, Ochieng AI. Thanks for listening, and we'll catch you next time.